Hi everyone. Today let's look at a classic problem. Integer to Roman. Opening. We are given a positive integer between 1 and 3,999, and we need to convert it into a Roman numeral. Roman numerals are built from 7 basic symbols. I equals 1, V equals 5, X equals 10, L equals 50, C equals 100, D equals 500, and M equals 1000. To keep the numerals short, Roman numerals also use 6 subtractive forms, where a smaller symbol is placed before a larger one to mean subtraction. These forms are IV equals 4, IX equals 9, XL equals 40, XC equals 90. CD equals 400 and CM equals 900. Our job is to take any number in the allowed range and write it as the correct sequence of these psi. Mabols. Naive approach. A direct way to solve this is to handle each decimal place separately. We build 4 lookup tables, one each covering the thousands, hundreds, tens, and ones. Each table holds the 10 Roman numeral strings representing the digits 0 through 9 in that PL. Ace. We then peel off each digit of the number, index into the matching table, and concatenate the 4 pieces. This works and is very explicit, but it requires 4 separate tables and does not reveal why the subtractive forms appear where the E do. We can do better with a single unified table and one greedy loop. Core idea. The key insight is that Roman numerals are formed greedily, from the largest value down to the smallest. We predefine a fixed table of 13 value and symbol pairs, sorted from largest to smallest. The table lists each basic symbol and also each of the 6 subtractive forms at its true numerical value. Then, we walk down this table once. At each row, we ask how many times the current value fits into the remaining number. That quotient is the repeat count. We append that many copies of the symbol, subtract the corresponding amount from the number, and move on to the next smaller value. Because the table already contains every legal subtractive form as its own row, the greedy choices never produce an illegal numeral. Key details. A few details keep the conversion correct. First, the table must be sorted strictly from largest to smallest, so the greedy scan always picks the biggest value that still fits. Second, we include the 6 subtractive forms, CM, CD, XC, XL, IX, and IV, as their own rows in the table, placed at the correct positions between the basic symbols. This is what lets a number like 900 be written as CM in one step, instead of pushing the algorithm into a corner, where it would have to append C 9 times, which is forbidden. Third, when a value is larger than the remaining number, the quotient is 0. So we append nothing and simply move on to the next row. Fourth, only the powers of 10, namely I, X, C, and M, may be repeated, and at most 3 times in a row, which the quotient naturally respects because any 4th copy would instead be caught by the matchee. Then G subtractive form higher up the table. Fifth, once the remaining number reaches 0, we stop scanning early since there is nothing left to convert. Walkthrough. Let's trace the first example. We start with the number 3,749 and we want to convert it to a Roman numeral. We begin by building the fixed table of 13 value and symbol pairs, ordered from largest to smallest. The table starts with M at 1000, then CM at 900, D at 500, CD at 400, C at 100, XC at 90, L at 50, XL at 40, X at 10, IX at 9, Vi at 5, IV at 4, and finally I at 1. Next, we create an empty result accumulator. Each greedy step will drop one piece of symbols into this accumulator, and we will join all the pieces together at the end. Now we enter the main loop and look at the first row of the table, M at 1000. We divide the current number, 3,749, by 1000. The quotient is 3, meaning 1000 fits 3 times, so the repeat count is 3. We append 3 copies of the symbol M, giving the piece M, M, M and add it to the accumulator. The accumulator now holds the single piece MMM. Then we subtract 3,000 from the number. 3,749 minus 3,000 leaves 749. The remainder is still positive, so we continue scanning down the table. The next row is CM at 900. 900 is larger than the remaining 749, so the quotient is 0. We append nothing and move down to the next smaller value. Now we reach D at 500. We divide 749 by 500. The quotient is 1, so the repeat count is 1. We append one copy of the symbol D and add it to the accumulator. The accumulator now holds two pieces, M, 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 and D. We subtract 500. 749 minus 500 leaves 249. The remainder is still positive, so we continue. The next row is CD at 400. 400 is larger than the remaining 249, so the quotient is 0. We append nothing and move down. Now we reach C at 100. We divide 249 by 100. The quotient is 2, so the repeat count is 2. We append two copies of the symbol C, giving the piece CC, and add it to the accumulator. The accumulator now holds three pieces, MMM, D, and CC. We subtract 200. 249 minus 200 leaves 49. The remainder is still positive, so we continue. The next rows are XC at 90 and L at 50. Both values are larger than the remaining 49, so each gives a quotient of 0. We skip past both rows without appending anything. Now we reach XL at 40. We divide 49 by 40. The quotient is 1, so the repeat count is 1. We append one copy of the symbol pair XL and add it to the accumulator. The accumulator now holds four pieces, M, 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 D, C, C, and XL. We subtract 40. 49 minus 40 leaves 9. The remainder is still positive, so we continue. The next row is X at 10. 10 is larger than the remaining 9, so the quotient is 0. We append nothing and move down. Now we reach IX at 9. We divide 9 by 9. The quotient is 1, so the repeat count is 1. We append one copy of the symbol pair IX and add it to the accumulator. The accumulator now holds five pieces, MMMDCCXL, and IX. We subtract 9. 9 minus 9 leaves 0. The remainder has now reached 0, which means the number has been fully converted. Since the remaining number is 0, we stop the loop early and stop scanning the rest of the table. There is nothing left to convert. Finally, we join all the pieces in the accumulator into a single string. The final answer is M, 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 D, C, C, X, L, I, X, which is the Roman numeral representing 3,749. Notice the structure. The greedy scan picked M 3 times, covering the thousands, then D once and C twice, covering the hundreds, then XL once, covering the 40, and finally IX once, covering the 9. Every subtractive form appeared naturally as its own row in the table, so the algorithm never had to reason about placement rules. It just divided, appended, and subtracted, moving down the table until the remainder hit 0. Complexity. The running time is constant because the table has a fixed size of 13 rows, and we scan it at most once. The work inside each row, a division, an append, and a subtraction, is also constant. The extra space we use is constant as well, since the table itself is fixed, and the result accumulator holds at most a handful of short pieces. So the whole conversion is bounded by a small constant, independent of the size of the input number. Summary. Integer to Roman comes down to a single greedy pass down a fixed table. The ideas to remember are these. Build a table of 13 value and symbol pairs. sorted largest to smallest, including the 6 subtractive forms. At each row, divide the remaining number by the value to get a repeat count. Append many copies of the symbol and subtract the matching amount. Skip any row whose value is too large and stop early once the remainder reaches 0. Thank you all, and see you next time.